everyone. Thank you very much for introduction. It's my pleasure to talk here. So my talk today is the application of MRI proton transfer MRI technique in neuro-oncology. This is my financial disclosure. First, I will talk about MBT6 imaging-based principle, and then I will talk current application of MRI to neuro-oncology. Finally, I will talk about the standardization and consensus recommendation. STES is a chemical exchange dependent serine transfer. This technique was proposed by Wall and Bauban at NIH in year 2000, and it's almost 23 years old. STES imaging is a normal MRI, molecular MRI technique that can detect some low concentration chemical, exogenous or endogenous, indirectly using water signal. The important thing here is, you know that our MRI scanner are designed to detect water. Now, you can use the same MRI scanner to see something else. Scientists in the field have published many important papers in the top journal. 2003, Nature Medicine, 2006, Science, and then Nature Biotechnology, PNS, and Nature Medicine again, and Nature Medicine, Nature Protocol, Nature Material, Nature Medicine, PNS, Nature Communication, Nature Biomedical Engineering, and several more in recent years. So what's the imaging? So you know, tissue has a lot of water, 70 to 80%. So this is why many standard MRI, T2 MRI, T1 MRI, FLAIR DTI work very well because high is enough. And the tissue has a lot of protein, 8 to 10%. And one MRI technique called MTC can detect a solid-like protein peptide, like a melanoprotein, nuclear protein. In the MRI proton transfer, imaging is designed to detect mobile cytosolic protein peptide. This is protein molecule. Yeah, this backbone. So MRI proton here, so means each protein has many MRI proton. And MRI proton exchange with water all the time. The average exchange rate is 20.6 at normal pH and reduced to 10.1 in ischemic brain. Another thing I want to point out is all the backbone MRI proton have similar MRI frequency, 8 to 9 ppm. Here in some other proton. So this is from the Ulrich textbook, 1986. So who got a Nobel Prize in chemistry in year 2002? So in the adult brain, use the specific MRI sequence. We have been able to see the MRI proton at 8.25 ppm here, in water here. So now you have MRI proton here, you have water signal here. The difference is 3.5 ppm, which is 440 hertz at 3 Tesla in my scanner. And then you put MRI proton, you put I radiation on MRI proton, and MRI proton will be saturated. And then saturation will transfer to the water, and then after a few seconds, MRI proton disappear in water and reduce significantly. So due to repeat saturation transfer process. According to the theory, proton transfer ratio, PTR, depends on exchange rate. through the concentration. So for ABT, this APTR, and this is the MR proton concentration. So the ABT imaging has two important applications. One is pH imaging, because the exchange rate depends on pH. And one important application is pH imaging of stroke, because in acute stroke, pH reduced 0.5 unit. Another application is imaging of protein. One important application is imaging of cancer, because many proteins are overexpressed in cancer, but intracellular pH, hormonal stem, and the cancer in the normal brain. So one the general question people will ask is, what's the ABT weight in my serum us? This is a very good model for ABT weight in my imaging egg white. So egg white, cytoplasm of egg, a lot protein here, and egg white has very high ABT weight in my segment, 10 to 20%. Water is 100, so this is huge. And cook egg white. So egg white become solid, and every signal is almost 0. So every signal is associated with mobile cytosolic protein and peptide. Now I talk about the application to brain tumor, from the tumor detection, grading, to differentiate tumor occurrence from cellular rate and predict tumor genetic marker like IDH, also MTMT. This slide shows the profile of hemoglobinoma and gadolinium enhanced area and peri-tumor area. So from these slides, you can see tumor core with gadolinium enhancement show much more protected species and much higher protein level compared to peri-tumor area. So the increased protein content and leaching might be associated with increased cellularity. So, and then if we have protein mine, so tumor core should still hypointense. This slide shows 3 examples of ABT-weighted imaging of brain tumor: grade 4, grade 3, and grade 2, and T2-weighted still hyperintense. Flare show hyperintense. And ABT shown hyperintense in grade 4 and grade 3, and isointense in grade 2. And gadolinium T1-weighted still green enhancement. Grade 4 enhancement, grade 3 is not enhanced in grade 2. So you can see the ABT show very similar feature is gadolinium T1-weighted. And you should keep in mind, ABT-weighted just use endogenous protein peptide. This is very good for some patients, also for some pediatric patients. This is setting therapy for brain tumor, surgery, followed by chemotherapy, radiotherapy. So this is very good for many patients. The problem is tumor recurrence. Anytime after treatment. At the same time, patient might have treatment failure. The early time called shield operation, and later time called radionecrosis. So in the clinical, how to separate tumor recurrence in treatment is very challenging. Case 1, case 2, treatment failure, tumor recurrence. So you can see both show very similar MR feature, enhanced hyperintense, mass effect, gadolinium enhancement. So you can see this issue in like a 50% patient clinical. And for this patient, in order to see if tumor free is good or tumor clearance, patient may need surgery or may need longitudinal analysis over months. But surgery is invasive, and longitudinal analysis take time. Patient cannot be wait. So this paper published in 1983, almost 40 years ago, by Peter Berger. He pointed out this problem 40 years ago, and this problem has not been solved very well in the past 40 years. So we try to use the ABMI to solve this problem. We apply ABD imaging to animal model. So this SAP. So this very good radiotherapy equipment for animal study. Animal put here. And then we radiate put polygrade into 10 by 10 square area. In the animal monitor monthly, and then 5 to 6 months, you can see T2 hyperintensity in gadolinium Hopkins. So this is tumor frame. It's not tumor. And gadolinium tumor with ABMI enhancement. And ABMI hypointense to isointense. Compared to the tumor, same thing. Gadolinium tumor with ABMI enhancement, what ABMI hyperintensity. So you can separate radial causes in tumor very well, low and high, very easily by your eye. So radial causes, ABMI low compared to the tumor, hyperintense. Radial causes in tumor show opposite ABMI signal. So radial causes in glioma can be distinguished easily by ABMI in Harvard patient. Case 1, tumor refract. Case 2, tumor occurrence. Flare, gadolinium tumor ABMI is very hard to separate one to another. However, ABMI isotense for tumor refract. Hyperintense, high signal for tumor recurrence. So the tumor refract, tumor recurrence can be differentiated by ABMI very well. This has been confirmed by pathology. Summary: every signal is consistently low in tumor refract and consistently high in active tumor. And tumor refract and active tumor can be distinguished easily by eye with ABT weighted MRI. So the 2007 WHO was based on tissue histology for tumor classification. And 2016 WHO for the first time used genetic marker to classify CNS tumor. In the 2021 WHO even more emphasized on the use molecular marker. So, so we have been sure that ABMI can help identify the tumor genetic marker, the IDH wild type, IDH mutant. So IDH wild type show high AP signal compared to IT mutant still almost iso-intense ABT weight MR signal. So this is still ongoing study. Finally, I will mention something about the APMI standardization in consensus recommendation. So currently, people can do the AMI on different MI scanner. So GE, Huipu, and Siemens. The problem is people use a different MI sequence, situation, and power. So currently, it's very hard to compare the APMI result between the vendor, between the lab. The leader in the field have worked together to propose consensus recommendation in published paper in year 2002. And the very important thing is that use 2 seconds in 2 microtesla. Conclusion: APMI can detect endogenous mobile cellular protein. It is totally non-invasive, can easily be transferred to clinical. So the APMI can provide important information for cerebral disease, brain tumor, stroke, AD, PD, TBI, pediatric brain development, and other disease. So doing the clinical APD imaging is a little challenging now because hardware limitation and time still a little long. And so there is a need for industry and academia to work together for APMI standardization. So we will recommend to use 2 seconds in 2 microtesla for the APD with MRI imaging of brain tumor at 3 Tesla. Thank you very much.